This is the...
All right, recording now. So,
All right. Kick it off, Casey.
Sounds good. So, hello everyone. I'm going to be doing a quick as I can demo of TensorflowJS, and just basically a simple walk through the code of a simple app, and sort of talk about some of the background just in case anyone wants to use it. They might have enough information to sort of navigate this stuff. It's sort of a challenging thing to present for something like a JS meetup, just because it's using JS, but it also uses a different, different domain knowledge. So part of what I'm going to try to do is go through what I think is the minimal background that you need for it. So at any point, if anything is unclear, just let me know and I'll stop and answer any questions. And I'll try to go through it pretty quick. I'm going to try to stick to 30 minutes. It might be hard to quite get that time, but just let me know if anything is confusing and I'll try to go over it again. So let me go ahead and start. So as I said, I'm going to present TensorflowJS. My name's Casey Wilson. What was that? Was there a question? Okay, so I'm going to talk about TensorflowJS, and TensorFlow. So this is the agenda for today. I'm going to first define what it is, talk about it. We'll do a demo of what we can do with it, and I'm going to do the demo first because if I jump straight into the technical side of it, I think there's going to be a lot of people falling asleep. So we'll do the demo first, then talk about some of the specifics, and then come back to the demo after that. And so after I do a quick demo of the little code that we'll be building, I'll talk about what machine learning is and give some more background and definitions. And then I'll sort of revisit the question, what is TensorFlow, with that new context. And we'll do a quick code overview, and then if you guys have any questions or any simple ideas to try, ways to change what this app is doing, I'll be open to it. So first thing, what is TensorflowJS? So this comes straight from the website. It's a library for machine learning in JavaScript. So let me click on this link real quick. So here's sort of the website. You develop machine learning models, and you can do it directly in the browser, which we'll do, and you can also use Node.js. And this is a pretty cool website. It's got some very cool tutorials where it basically walks you through doing some pretty neat stuff. This particular thing that I'm doing is based off of one of the tutorials, but it's got some slight changes to it. Also, TensorFlow is originally a library. It's made by Google. It's originally made for Python, and Python is still sort of the default for TensorFlow and for, I would say, machine learning stuff in general. So Python still has some benefits over TensorflowJS, mainly performance benefits. It's faster, but TensorflowJS is very cool because it's nice to be able to do this stuff in the browser. And it's also cool to see it in JavaScript. As I have become more of a JavaScript developer over time, it's nice to see some of this code in more of a JavaScript style. So that's what TensorFlow is.
Casey,
yep.
Would you rather us hold questions to the end?
No, go for it.
Are the performance benefits to do with NumPy, or what's the origin of the performance benefit for Python?
So for example, what we're going to do is going to run in the browser. So it's going to be running sort of higher level. But yeah, Python uses NumPy, which compiles to C, I think. And it's just basically super fast with matrix operations, which is pretty much the main computation for this. And it also, I don't know if TensorflowJS has support for GPUs, but basically you can train models like up to thousands of times faster on GPUs than you can on CPUs, and Python's TensorFlow supports that very easily. And if you go to like any AWS, like SageMaker or the Google equivalent, they'll have some like GPU support. Something else I won't get into is Google actually made a specific type of like hardware device called a TPU for TensorFlow for it to run super fast. But yeah, good question. And so essentially, it just provides a simple interface for building machine learning models. So if you're a JavaScript developer, it would be equivalent to React performs a simpler interface for, you know, dynamic DOM updates. Express makes a simpler interface for creating APIs. So TensorFlow does that for machine learning models. So I want to do a quick demo first of what will be sort of what this code is building. And I deployed this right before here on GitHub. So if anyone wants, you can check out this link at the end. See, and you can like try this on your own. Where is chat? All right, so the basic idea is 3 buttons. We've got, let me make sure the page is refreshed. So we've got a button that says red background, green background, background noise. So when I click a button, so if I click red background, it's going to start recording audio. It's going to start recording audio samples of whatever I'm doing. And then same thing with green background. And then this background noise is going to be something separate. But the red background, what will happen is whatever noise that I'm making while that button is pressed, it will start collecting those samples, and eventually it'll use those samples to recognize that sound. And after we've gone through a training process, we'll be able to, it'll change the background of the website to red. Same thing with green, so it'll be 2 different sounds. I'm gonna whistle for red and snap for green, and just gonna whistle because you can do words, like I could say red, 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 green, green. I may do that at some point, but it's easier for it to differentiate between, those are 2 like more different sounds. So basically higher chance of like correct success. And then there's this other button, background noise. And that's just, I'm gonna press that button and sit silently so that it picks up whatever noise is happening in the background here and doesn't think that any of the background noise is what's causing any of these. So I'm gonna go ahead and start doing that. You wanna ideally collect the same number of samples of each one. When I click a button, it'll say how many samples are up here. So we'll start with the red. So I want it to be so that I can train this thing that whenever I whistle, it'll show a red background. So let me collect the data for that first. Cool stuff. I hope somebody fast forwards to that part of the demo. So, all right. So I got roughly a little over 200 of each. I was talking a little bit at the beginning of the green. That might mess it up. So I'm just going to sit silently for 200-ish samples for the background noise now. All right, caught some dogs barking in the background. So I'm going to train it, and it's going to go through multiple rounds of like learning these things. It'll spit out what, for each round, what the percentage of correctness is. So it's going to go through 10 rounds here. And they generally trend to getting better. Sometimes it will dip back down. But also,
Casey,
yeah, go ahead.
Sorry, I had one question here. For the training stuff, is this stuff blocking the main thread, or does it get offloaded to like workers or something?
I'm 99% sure that it would be offloaded.
Yeah, cool.
Like, I don't know that I've read it for a fact, but I mean, there's definitely stuff happening in JavaScript, but this this would not be something that I think would primarily be JavaScript working. All right.
Cool.
So we trained it through 10 runs, basically, ended up with 84% accuracy. So when I click this listen button, if I whistle, it should turn it red. And if I snap, it should turn it green. Also left from the original tutorials, this little slider thing, and it'll slide in those directions as well. But all right, so quick demo of just basically what we're going to be doing. So as I'm sort of going through this, or maybe you already do, if you have any other ideas, like it will do this for any noise. And some noises are going to work better than others. I chose whistling and snaps because they're fairly different. But if you have any other ideas at the end, I'm happy to try them out. If anyone wants me to sing, I'm going to recommend that you do it. So that's the only thing here. All right. So any questions about that little simple website thing before I move on?
Do you have any indications on like what the limitations are for doing what sort of models you can collect in the browser? Are you going to talk about that?
So this is just going to be like a deep learning convolutional neural network models. You should be able to do anything that TensorFlow can do.
Okay.
So I guess no, there's not really a limit to the models. I mean, a limit would be a method like this. You're going to not collect much data. So it might work for a simple task like this. It's not going to work well for, interpreting speech. But yeah, you can do pretty much anything. Again, this is, I think you could develop some cool features with this, but it's more interesting than anything else. I still think if you're going to make like a production thing, you'd probably use something that can do more heavy lifting. And you probably need, you definitely need a lot more data.
Just as a minor thing, but between the red-green call, what was the threshold? Like how sure did it have to be to decide it was red?
It only has to be the top percentage. So it goes through every, I think I set it to 100 samples, and I'll show some of this code. It'll go through like 100 samples, whatever the mode is for those 100 samples is what it predicts as the last sound that it just heard. But basically, each individual sample is predicted by, it's an array at the end, and the array has 3 values. Whichever of the 3 values, like the first element would correspond to red, the second green, the third background noise. They add up to 1, but whichever one has the highest probability is the one that it predicts it as. So there's not like a threshold in that way. It's just whichever one's the highest.
Thank you.
All right. So I want to talk a little bit about showing that what machine learning is. And then I think with that extra context, we can start to look at the code. I think before talking about some of this, a lot of the code would probably not be super useful or meaningful. But I just got 2 definitions that were top Google hits. So one is from Wikipedia, study of computer algorithms that improve automatically through experience and by the use of data. And then another from SAS.com, method of data analysis that automates analytical model building. So basically the takeaway is that it takes data, takes some type of information, and it uses some statistical, usually iterative statistical technique to make either a prediction or a classification. And so this is my little addition here. Sort of the motivation, like when you would care about using it, is it helps make sense for problem domains where there's no obvious roadmap to define how you do something. So like, certain problems, I can't say, if I have this value, then do that. If I have this value, do something else. So that's sort of where machine learning comes in. So it's often for like non-deterministic things where sometimes the answer is not necessarily clear. Sometimes you want more of a percentage, a likelihood than, I can input something into a machine and know that it's exactly this thing. So just some examples of types of things that would be good for machine learning, hard for, if you're just a programmer trying to write a program for it. So if you get a picture of all donuts or all tires, how do you classify that it's a donut or a tire? All you've got is the values of pixels in a picture. So it would be really challenging to, or honestly, it'd probably be impossible to get anything more than like mediocre accuracy if you tried to make like some method that said, if this pixel value is this, then do this. It would be a huge amount of code, and probably you'd never get that good at it. So another one would be like house value. So get bedrooms, bathrooms, square feet, and zip. So if you wanted to predict a house value, make a prediction about something, that's called regression, which we're not going to do today. But if you want to basically find out what category of house it is, that would be classification. So say given bedrooms, bathrooms, price, blah, 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 make a prediction. Is it an apartment, townhouse, house? So that's classification. And then the last one is closest to what we're doing. So what words are being spoken in an audio file? That's classification. It'd be really hard or impossible to, look at a binary file and determine what words are being spoken. And so the essence of what machine learning is classifying or making predictions through using iterative techniques. And one like fun fact is a lot of times these the questions that you solve with machine learning tend to be problems that are pretty easy for people, which is sort of interesting. But a lot of the times, we're really good at doing these things. We don't have to think about it. We don't know how we're good at doing it. We have a vague idea, but we don't have an algorithm of how our brain can tell us that it's a donut or a tire. So these solve these type of problems. So specifically what we're going to focus on is supervised classification. And so we already talked about classification, but supervised is, as opposed to unsupervised learning, is something where you give a machine learning algorithm data, samples, and you give it labels. So you already have like a type, you have a label for the sample before you do anything with it. And so it basically tries to draw a curve on a graph to classify those labels. So like, for example, in this housing price example or housing example, the label would be the type, and these would be what you use to predict the type. So this would be like an example of a supervised data set, like supervised method, where we know that this is an apartment. We know this is a townhouse. So we want to draw a curve that separates those things. And then we'll get some visuals after this, but just a couple of simple terms. So samples, when you hear me refer to samples, that's basically talking about a row. So each one of these rows is a sample. And features are basically the columns. So square feet, bedrooms, all the way up to type are all features. So yeah, any questions at the moment?
Can you take one model set and apply? Do you get any benefit from taking a single model set and applying different labels to it, or trying to get different vectors out of it?
So are you saying
like type right here is your label? Like, what if I was interested in maybe median education, or some other or demographic, or some other ancillary piece of data that could be learned from this? Do you get any benefit from taking one model set and running it through different types of labels or against different types of labels?
You would get benefits of using the same data doing that. Probably less benefit if you use the same model. Like if you train a model to learn apartment, and then you said, all right, model, tell me what the demographic is of this person. They're probably not very good at it.
Okay.
So there are two basic types basic types of classification. Almost always it's going to be the second, which is nonlinear. But basically, with machine learning, you're just trying to draw a line or a curve through different classes to tell them, you know, is it this class or that? So if you imagine, we'll take square feet and price. So imagine the x-axis is square feet, y-axis is price. The machine learning model is essentially the line or the curve that separates those classes. So the learning process is teaching that model where to sort of draw the line. And I mean, if you ever get a linear model in the real world, you probably can solve it with like if then else kind of things. So pretty much anytime you ever see anything, it'll be nonlinear. And it's worth mentioning that like in the real world, for the vast majority of problems, there's no perfect separation. So like if you, even if you like draw the best possible curve to separate these classes, so say again, this is still housing type, you're still going to get some errors. It's not going to be perfect because the world is too unpredictable. And really, I mean, any problem that you ever have outside of like a lab setting is going to have that issue. So real quick, let me show what this looks like. So it's iterative. Machine learning is iterative. So you start with like a random line or a curve, and you keep running the same thing over and over, making slight adjustments until eventually you get something that you decide is good enough, or say that it's run for a long enough time. So this is an example of what like a training process might look like, trying to separate these two classes. So eventually, you know, it'll get to a place where we'll say that's good enough, stop. All right. And so this is another important one. This is sort of another view of machine learning. It's this view, these graphs, or this plot is more of, I would say, a mathematician's view. This directed, connected graph is more of the computer scientist view. They both exist because they abstract different things in the domain. But pretty much this is the machine that you use to determine how the actual like classification process happens. So from this view, these starting bubbles are essentially the features. So that would be square feet, bedrooms, price, all that stuff. So you start, you know, x2 might be price, x3 might be square feet, xn might be bedrooms. So basically what happens is you take these features, you pass individual samples through them, through these what are called inputs in this view. And you have this starting random set of weights that you pass into a function. So you could just imagine this function is like a JavaScript function. And you're passing into it an array of samples. And you're also passing into it these W's, which are the weights, which are essentially just arguments to the function. But they start off as random numbers. And what the process of machine learning does is it passes it through this function, puts it through another one that basically makes it make a guess as to which the class is. It gets this y-hat, which is the prediction. And based on the prediction and how we determine how the prediction is right or wrong, it updates these W's to make it a little bit closer to what we expect. So this is sort of a more generic view of like, you could sort of say almost any machine learning algorithm would look sort of like this. So sort of recap here, the training phase of machine learning is when you're creating these weights, you're giving them the values that make good predictions, and you're drawing these lines and curves. And the only thing that you need to do that is, you know, these are just two functions that you give it an input and it spits out an output. The output is determined both by the samples, but also by the weights. And so the training phase updates those weights so that the function makes good predictions. And so then there's the testing prediction phase where you take a trained model. So you basically take that already drawn curve and you give it new samples it's never seen, and you see which side of the line or curve it falls on. So that's the first part of the intro for machine learning. The next part has a little bit more to it, but it's not too bad, I don't think. But before I go on, do you guys have any questions about that? Okay. So, quick recap here. These are the two views. Got the plot view, and you also got the connected graph view. So the sort of the category of machine learning algorithm that this demo uses is a neural network. So a neural network is a specific machine learning algorithm that combines inputs into new layers, which basically creates, it does a couple things. It makes multiple, it runs multiple machine learning algorithms at the same time, but it also functionally creates new sets of abstract features. So if you look back at this view, this is like a single machine learning algorithm, maybe a linear regression that you pass through, like some activation function, a sigmoid. So what happens here is you can sort of view each of these as one individual machine learning algorithm. So, you know, these three inputs connect to this hidden layer, that's one. These three inputs connect to this hidden layer, that's two. So you repeat that, you now have 5 of these. With the added benefit is that you can sort of think of this recursively as not only are you generating a new machine learning algorithm each time, but there's no reason to treat these hidden inputs any differently from these original inputs. So it basically creates a new set of more abstract features that are better for the predictions. So basically this first layer is good for us. This is how we understand things, inputs. You know, we can talk about housing prices and square feet and stuff. The hidden layers are good for the machine. The machine takes the information that it cares about to make the predictions. So that's basically what this says. So another layer to go into that, deep learning is essentially, I would say probably the main reason why machine learning has been hyped the last decade. But it's the same thing, it's a neural network. The only difference is deep learning generally implies there are multiple hidden layers. A neural network can be, you know, 1 or 0. So same thing though, you take an input, it creates more and more abstract features over time and then makes a prediction. So like by the time you get to this last feature set, you know, there's probably no connection that you can easily make between, you know, this is square feet or this is whatever, because it's applying a bunch of functions over and over again. And it created something new.
Is there orders of magnitude more effort involved in developing models for deep learning as opposed to just your single layer neural network?
Yes. And don't ask me the specifics, but I think one of the, like, machine learning is always like come and go in phases of popularity. One of the original problems of neural networks is they didn't have good mathematical methods to update things fast enough until 20 or 30 years ago. So like it wasn't not only that the technology wasn't there, but there also just wasn't, they didn't have the methods yet to make it feasible to update something with that many layers. So yes, it can definitely make an exponential difference. So this is sort of the last addition of this stuff to neural networks. So this is getting into the territory of what we actually do in this code. So there's a classic data set called MNIST, it's already 5:30, that you train, or that basically it's an entry level like way to teach people generally machine learning stuff. It's, you know, these black and white images of numbers that are generally normalized, so they're like centered, all the same size, that kind of stuff. And so with these, this becomes an image classification problem. In machine learning, the features are individual pixels. So it's got all the MNIST data sets are 28 by 28. Each pixel is a feature. So it's got 784 starting features here. But there's a problem, which is an individual pixel doesn't really give much value as to what the picture is. So if I said, give me the 10th row and 10th column pixel for each of these, you know, that doesn't mean anything. It's probably like whether or not it's black or white may or may not have any bearing on like what the actual image is. So the better solution to this is you need to make a combination of multiple features that are closely related. So it's not the 10th column, 10th row. It's the 10th column and 10th row plus all of the other pixels directly around it or something similar. So that process is what a convolutional neural network does. So it combines not just individual features, but it creates features out of combinations of like neighbor features. It's generally used for image classification. It's also what we use, or what I use for this. And like I said, it's more useful when individual features have less meaning than within the context of their neighbors. But yeah, like an individual pixel's RGB value doesn't really mean much. It's not going to give much value. So just a sort of graphical view of what that looks like, how you do that. And I'm going through all of this so that we can sort of see and know what I'm talking about a little bit in the code. So this is the code that does the convolutions and the layers. So you take a starting image, you apply a filter. It's called either a filter or a kernel. And this is the same kind of filter that you use to like filter images, like an Instagram filter or whatever. The only difference is the numbers inside of this filter are different. But basically what a filter does is it takes an image, passes usually a square through the, so you would like multiply each individual value in this square with each individual value in this square, average them, or do some mathematical operation. And that result is now a new pixel in a new picture. And so you repeat that process, you just move down the line, start with the first 9, then you do the next 9. You repeat that all the way until the end. So that's the process of convolution. So you're basically creating a new image out of combinations of the features of old images. And again, same as with the weights from before, these start as random numbers. As time goes on, the algorithm gets better at telling you what those numbers should be. And then after that, it does what's called a max pooling. So it'll maybe go every 4, it'll do another filter where it'll skip, instead of running one by one, it might skip some and make a smaller image essentially. So all this does is make it so that at the very end, you know, we don't have 784 features, maybe we have, 50. And so you do the convolution to generate a new image, then you do the max pooling to make it smaller. So you can see it goes from 28 by 28. When you max pool, cuts it in half. Then you do another convolution. This is sort of generally how this works. And then you do another max pooling. And then you do what's called flattening it. So you take the square and then you separate all of the pixels so that they're flat, so that you can put them into an input that looks like this. So basically a one-dimensional array or vector. So that's the process of convolution. And at the end of the convolution process, you put the new abstract pixels or features into the fully connected neural network, which is just the regular deep learning neural network. And I'll talk about it a bit in a minute, but that's just sort of what this code here does. So I'm starting with a convolutional layer. I'm saying apply 32 filters. After that, do a max pooling. So it cuts it in half. Do another convolutional layer, another max pooling, flatten it, and then connect it to dense layers. So dense is just what you call a regular neural network, and then make a prediction. So that's what that code's doing. So with all that context, just to ask the question again, what is TensorflowJS? So it's a library that provides common functionality for solving machine learning problems, but with a particular emphasis on deep learning. And yeah, again, it can be run browser or in Node.js, but it just gives it, like, you can imagine if you had to implement all of this from scratch, it would be just an insane amount of work, not only to just get it working, but you'd have to know the mathematical functions to like do back propagation. You'd have to be able to optimize it. You'd have to like compile it to a low level language. It would just be too much task or too much work for anyone to do. So cool features of TensorFlow JS in particular, you can train in the browser. You've seen that. You can also do it on Node.js. You can serialize models. So you can save them in local storage or file storage or whatever. And we'll save one to local storage later. And it's also just got some cool, there's a cool online labs. So any questions about that technical stuff? So the background part is over.
What's the, well, I don't know if relationship's the right word, but what is the guiding factor for how many hidden layers to use in a given neural network?
That's the $1 million question. That's one of the many reasons that it's really hard to do, because there's not always an obvious way to do it. And there, you know, people will spend entire careers finding ways to like optimize that. I mean, you can literally optimize that, use a machine learning algorithm to find the answer to that question. So I would say a lot of times there's no, people can like learn their heuristics for certain things in certain domains, but it's hard to answer that question. And that's one of the main problems with machine learning and deep learning in particular, I think, is, you know, it can almost be sort of random seeming. There's, you know, people can do like good approaches to it, but you know, it's not always obvious. But yeah, that's a very good question. And if you answer it, you'll probably be at least famous, if not rich and famous. So, all right. So the goal, we just want to train a convolutional neural network on audio data based on a tutorial that's on TensorFlow. We want to classify new audio samples that the model has never heard, and then we'll store it in local storage for later. So we've already seen that once, but just to sort of state what we're doing again with the new context. So let's take a quick view of the site code first. So there's not going to be anything like particularly crazy happening here. It's a very simple site. So we got some buttons where you red background, green background, and background noise. I'll call this function collect, which collects data. You got a train button, which calls a train function. Listen, which calls a listen function, which waits for new inputs to predict. And then later on, if there's time, we'll do a save model and a load model where you can save and load to local storage. And yeah, I think that's everything of particular interest here. There's a little like global toggle to say what the state of various things are in. Okay, and then I think there's one more slide. All right, so the last little bit of technical info. We're not going to go into the specifics, but so we're using a convolutional neural network that's usually used for visual data, so images, but we're recording audio data, which is an array of numbers that represent a sound wave. So what one functionality that TensorFlow gives is creating an image out of audio. So that image is called a spectrogram. And so like this is, for example, this is a spectrogram of playing guitar. I don't know what it is, but it looks like it's just some chords, but you can sort of see how like there are intervals, relatively set intervals over time where like things are happening. This spectrogram was generated with Python. So like, we're not gonna see any spectrograms of the recording that we're doing, but just for your knowledge, this is what a spectrogram looks like. And so it's gonna be, the algorithm is gonna be doing a classification of a spectrogram to make a prediction about what the sound is. So like the spectrogram of a whistle would look different from the spectrogram of a snap. Okay. So any questions before I go over the JS code? I think we'll be able to finish up before 6. All right. So basically, we're going to collect discrete frames of data, one frame. So a frame is a sample in this case. So sample being a row. So each individual frame will eventually be a picture. That's a row, that's a sample, and it's around 23 milliseconds of audio. So that's what we're trying to do. And we are getting a model from TensorFlow. This already has some pre-trained stuff, but we're not using any of the pre-trained stuff here. We're saving it. We got some globals up here. And so we want to build the model. So this is sort of where you build the neural network. So you just declare, this is sequential, add these layers in the order that I specify them. So, you can see I go through the convolutional layers, conv 2D, max pooling 2D, and you specify the kernels or filters. So the number of frames is 3. So we make a 3x3 filter. So that's what's being specified right here in kernel size. It repeats it 32 times, so it creates 32 new images. And it moves one to the right whenever it creates one, and it moves one down, one to the right, one down on the next. And the padding same just essentially means that it creates an image of the same size as the original image. Then it does the max pooling, which cuts the image size in half, does another convolution, another max pooling. You specify an activation function. So this is just a function that says how to make a prediction based on what the values are. And after that, after the last max pooling, we flatten it. We pass it into a dense layer. So we pass it into this thing. Just for fun, I give it a different activation function. And then the very last thing is you make a dense layer. So one of these layers where you're predicting the output. The function for predicting the output is the softmax. So basically what this would look like is the convolution layers look very similar to this image. However, the dense layers, there are only 2. So there's only one here. And then the next one is the prediction layer. And that's a pretty standard architecture for convolutional stuff. So do that. This optimizer is basically how it says to update if something goes wrong, or to update based on how wrong you were. And then you compile it, you say the metric that you use to classify, to get a score is accuracy. This is the loss function. It says how far away you were from the truth. So yeah, you build the model, save it in a variable up here. And so this would be, I'm whistling and then collecting samples, and then it would run through that model eventually when I train it. So so if I look at the collect function, collect. So basically the collect, I'm just going to go through this very quickly. It takes the model that does the listening. It says to listen, generates a spectrogram, normalizes the spectrogram, which basically just means that it creates an array of samples and it gives them an average of 1 and a standard deviation, or an average of 0 and a standard deviation of 1, just so that there aren't any extremes in the data set. And then there's this examples array where it just pushes to this array. This array is what is used as the inputs to the training algorithm. So that's equivalent to the samples of the housing data over here. So that's the essence of what the collect function does. And you may remember as it's going on, it says how many samples it's collected each sample being 23 millisecond chunk of audio data. After you've collected it, you do a train. So it takes that audio model, or it takes the audio examples, and it passes them into that model that we shaped earlier. So this thing, and then it does training. So it basically draws that curve. And once it has finished, it runs through the entire data set 10 times, 16 images at a time. And once it's finished, then it just logs the accuracy of the epoch. And then I think the last thing to show is moving the slider. Oh yeah, listen. So after I've trained it, I click listen. It's listening to make a prediction. So all listen does is it does more or less the same thing as train, like it gets a spectrogram, normalizes it, but now it makes a prediction. So you asked earlier, I don't remember who asked, but what's the threshold that it decides that it's this or that? So essentially the threshold is it makes a prediction of one of these three classes. It's either red background, green background class, or background noise. So, you know, this probs would return an array that looked something like 0.5, 0.25, 0.25. And so that's what this probs would look like. And then this just takes the max of it. Whichever the max is, that's what it says the prediction is. So it says, in this case, it was this first class. And so one little extra thing, so it calls this move slider function, which is what actually updates the UI. And the move slider, I don't run it for every sample. I run it for every 50 samples. So I basically just get the mode. So it doesn't like switch to red and green instantly every time. So every 23 times 50 milliseconds, which maybe is a quarter of a second or so, it makes a prediction based on the mode, so the most common of the set of guesses. So if the guess is 0, turns the background red. If the guess is 1, turns it green. If it's 2, it turns it white and puts the text waiting patiently. So that's it. That is the grand tour. I don't think that there's anything else that's worth getting into that wouldn't be just extraneous details, but yeah, so does anyone have any questions or have anything that they'd be interested in trying?
So on this, what you have on the screen right now, so by possibly adding more convolutions or pooling, that is one of the triggers you can have to increase the accuracy of this model?
Maybe, but not necessarily.
Okay.
So, I mean, eventually, so two things. One, if you add more and more layers, if I added like 8 layers, maybe eventually it would be better, but it would take a lot longer to get there because it has to update a lot more weights. But also not necessarily. And in fact, you'd probably be more inclined to something called overfitting, which instead of learning like the essence of the problem, the model essentially memorizes the data set. So even though it's perfect for the data set, you might get 100% accuracy. If you give it a new sample, it's drawn the lines too strictly so that it only works for that data set. That's also possibly likely if you added too many layers, but honestly, it'd probably just take a really long time.
So is part of like building your models, is it part art as well?
Oh yeah, for sure. It's part art, part science, part random. It's just like trying stuff out.
Okay.
And one of the challenges I think with doing this stuff is it's very computationally expensive. It like, you don't get instant feedback like you do, you're like programming something. But not only that, if you're doing this on a production scale, you're probably either going to be paying for a service like AWS where you can scale it up indefinitely, or you've invested probably many thousands of dollars in your own like setup, but you're also paying for the electricity for that. So it's definitely got some barrier to entry problems. It's not as easy to enter anything but toy problems unless you're willing to pay for it. So that's a definite downside. Yeah.
Cool.
Yeah, good questions.
I was going to ask you, what do the models look like that come out?
Oh, do you want to see what they look like?
Sure. Or if it's, you know, if it's binary, I guess not. Is it just the weights? Is that all it is?
It's the weights. What is the other part? I don't know. It saves like 4 things. There's some JSON, there's some binary. It saves in different formats on the file system versus local storage, but let's actually save it in local storage. So I didn't mention this, but 2 more functions, save model, which saves in local storage. This is just something that TensorFlow gives you. So if you were building a website, someone could train, you could like train on their voice data or something, and then you could store that in local storage. And whenever they get back on the website, they already have a trained model. So we'll save the model. So let's just name it TF1. So click save. Didn't give any feedback, but let's check out what local storage looks like. So this is the format that it saves the model in. So it's got a topology, it's got metadata. It looks like these are, so it looks like the weight data is binary. And the topology, so basically the network architecture is JSON. And basically, I think all the metadata type stuff is JSON, but the actual weights, those arguments that you put into the function, there's too much there for JSON, so it's converted to binary. Yeah, good questions. So like with this, you can, you know, it's serialized. You can save this anywhere. You could store it in S3 or whatever and import it whenever you want it. So you could always sort of have those things around. Yeah, good stuff. So has anybody got anything else?
Just out of curiosity, does TensorFlow support this concept of, like you used Express before as an example? Does it support the concept of middleware or extensions or plugins?
I actually don't know. I'm gonna guess. I mean, probably something has been developed. I wouldn't say that from my knowledge, it's like part of the standard setup. Like with Express, you're probably using some type of middleware. With TensorFlow, I'm gonna guess, like you're probably using external libraries, but I don't know that it would like, I don't know that they often like plug in, you know. But yeah, good question. I don't have the answer, or that's the best I got. Anything else? Anybody got any cool ideas here? If not, I'm fine. Fine to end it there. Some whistles.
I'm just curious if an example like this would be able to, you know, tell the difference between different people speaking the same person's name or something.
Probably. You'd probably have to do more training data though.
Okay, so you could identify the speaker essentially.
Yeah, and it's a harder problem, but like, you know, I can, if I say red, 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 green, 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 it can do it. It's just not quite as good. I might as well show it. So red, 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 green, 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 green. All right, so let's train that. And probably the accuracy won't be as good as the whistles and the snaps. This one is also, it's more random. Like sometimes it does a decent job, sometimes it really doesn't. 38 going down is not a good sign.
So you're saying here is where you'd want to have more data to help with that?
Definitely.
Okay.
Most deep learning like is a very like data hungry model. That's one of the major downsides of it. It needs like very, very large amounts of data. And this is very much the complete opposite of that. You know, 5 seconds of me whistling or saying red or something. This isn't even worth trying. 38%, it's just going to do random stuff. But I mean, sometimes if I do the same things multiple times, for whatever reason, it does it better. I'm actually interested to see red, 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 green, 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 green. So let's see if we can beat 38% or whatever it was. But yeah, you could use this to like classify different people. You just need more data to ensure that it worked well. Yeah, I don't think this one's going to be much better. But
while we're watching that train, I didn't quite catch what the slider is showing us.
yeah, the slider is kind of a leftover from the actual TensorFlow tutorial demo. But basically, where is it? I haven't paid attention to it much. I just kind of left it there because it doesn't hurt anything. But it just sort of moves. If it's the first class, it moves down. If it's the second class, it moves up. So, I mean, same thing as the red-green background. It's just a moving slider instead of red or green.
Oh, okay.
Yeah, this isn't going to be any better if I listen. It's just basically making random predictions. Red, 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 red. Yeah, nothing. But if I load the model, what was it, TF1? So let me refresh this and load TF1. So this is the one with whistles and snaps. So done. So I can now listen. So it has the data for whistles and snaps. So that's pretty cool. I mean, that's a pretty cool feature, I think. But,
Nice.
anybody got anything else? It's 6. So gone an hour for a 30-minute presentation, but has anybody got anything?
No, appreciate it. Thanks for doing this.
Yeah, very interesting.
Cool. Thank you guys for joining. It was nice to have an audience for it. And then, yeah, feel free to like mess around with this on this link. Probably, I'm gonna guess that because there's like background noise happening on Zoom, it wasn't doing as well for the red-green stuff. Try it out on your own. Just make sure you get relatively similar numbers of samples for these, and you'll be able to do some predictions. And the code's also on GitHub. If you want to like mess around with it, you can add more classes and do different stuff. So I think that's it for me. Thank
Awesome.
you
Well,
guys for joining.
Yeah. Thanks again. That was great. Great demo and great talk.
Cool.
Thanks,
Thank
Casey.
you guys.